Look at this. How cool is that? The key to having a texture on your model lies in something called barycentric coordinates. I want you to imagine a triangle. Now pick any random point inside it. We need a way to describe exactly where that point is relative to the three corners. Think of it like a three-way tug of war. If the point is right in the middle, all three corners are pulling with equal strength. If the point is really close to the top corner, that top corner has a much stronger weight or influence. Every pixel has its own unique set of these three weights. This is crucial because it allows us to blend data. If a pixel is 90% influenced by the red corner and 10% by the blue corner, the resulting color is a 90-10 mix. That is how we get smooth gradients if we need it. When we apply textures, like painting a picture onto the triangle, using those weights directly, we get what's called affine mapping. Now let's talk about the image itself, namely UV mapping. You might ask, why U and V? Simply because we already used X, Y, and Z for the 3D space and we need new letters. Think of UVs as the coordinates on a piece of wrapping paper. 0, 0 is usually the top left corner, and the 1, 1 is the bottom right. It depends on your graphics API or the libraries you are using, but mathematically it doesn't matter. By assigning these coordinates to the corners of our 3D triangle, we are essentially pinning the wrapping paper to the geometry. The math we just discussed fills in the rest. Now look at the cube's faces. They are squares, right? But computer graphics cards hate squares. They love triangles. That is because a triangle is the geometric atom. It defines a flat plane perfectly and cannot be bent. To make a square face, we actually synthesize it by gluing two triangles together along diagonal. Our job is to ensure that texture flows perfectly across that invisible seam, fooling your eye into thinking it's one solid square surface. For our textures, I don't want to implement image loading, so let's create something procedurally. Just a simple two-dimensional array filled up using pure math. The first pattern is stripes. We don't care about X at all here. We just look at the vertical position, the Y coordinate, and use a modulo operation. We basically ask, when we divide the row number by 16, what is the remainder? If it's small, we paint it red. If it's big, we paint it yellow. That simple mathematical question creates perfect repeating horizontal bands infinitely, without ever having to draw a line by hand. Next is checkerboard. It's just a simple grid formula asking, is this row even or odd? And that alien-looking green and red pattern, that is classic XOR texture. We take the binary bits of the X position and the Y position and smash them together with a logic gate. It creates a complex, fractal-like design from a tiny line of math. Talking about affine mapping, it's fast, but it's flawed. When the triangles tilt away from you in 3D space, the texture looks wobbly and distorted. It looks like an old video game from the 90s, like PS1 game. Why does that happen? Because the screen is flat. It doesn't inherently know that the top of the triangle is further away than the bottom. To fix it, we have to perform perspective correction, something that was not possible tens of years ago as it involves division, and division is quite computationally expensive. We have to mathematically shrink the texture data based on how far that specific part of the triangle is. We divide the texture information by the depth at every single pixel. It's a bit more math for the computer to chew through, but the result is stable, a realistic image that looks like it actually exists in 3D space. In the previous video, I explained how to approach the cube and its rotation. You can watch it if you want details, but let me quickly summarize it. At its core, 3D graphics might look complex, but it really boils down to connecting dots with lines. To build a model like a Rubik's Cube, we start with simple square defined by vertices and edges. The magic happens when we want to move that square. We use trigonometry, specifically sine and cosine, to calculate how points travel in a circle around a pivot. By applying this logic to the X and Y axis, we can rotate shapes on the screen, but that's really just spinning a flat image around the Z axis. To step into the true third dimension, we introduce the Z axis for depth and upgrade our squares to a full cube using vertex and index buffers. Surprisingly, Rotating this 3D cube isn't some new, scary math. It's actually just 3 two-dimensional rotations stacked together. For example, spinning a cube like a top means rotating the x and z coordinates while keeping height constant. However, simply drawing lines isn't enough. Without rules, the computer draws everything at once, making the back of the cube appear on the top of the front, creating a massive visual. To fix these visual glitches, we use a technique called backface culling. By calculating the normal vector of each face, imagine a line sticking straight out of the surface. We can tell the computer to ignore any triangles pointing away from the camera. Finally, we create a sense of reality by adding perspective, which is achieved by simply dividing the object's position by its depth, so that things further away appear smaller. Once we ensure our math uses clean, original values for every calculation, we get a perfectly rotating, perspective-correct 3D cube rendered from scratch. So let me combine all of it together and use our newly learned texture mapping for our rotating cube. If you feel like it, you can add controls to switch the textures. Beautiful. Well, we still have some time, so let me show you one more thing. Lightning. Even with perfect perspective, every side is equally bright. It doesn't matter if a face is looking at the sun or hiding in the shadow. It's all at 100% brightness. To fix this, we need lightning, specifically flat shading. This is a great technique to start with. The math here is actually quite elegant. For every single triangle, we calculate a surface normal. Imagine an arrow sticking straight out of the center of the triangle, perpendicular to the surface. This arrow tells us exactly which way the face is looking. And sounds familiar, right? Because we did exactly that for backface culling. We can actually reuse the result of the computation. We compare that arrow to the direction of our light source, which in this code, in our example, is just the flashlight pointing straight forward from the camera. We use an operation called the dot product. It compares two vectors and gives us a single number from 0 to 1. If the triangle is facing the light directly, the result is 1, maximum brightness. If it turns sideways, the number drops. If it faces away, it hits 0, it's total darkness. We take that number, let's say 0.5, and we pass it into our pixel drawer. Right at the very end, before we put the pixel on the screen, we multiply the red, green and blue values by that 0.5. It's a simple multiplication, but it instantly adds volume. Your brain suddenly understands the shape not just by its outline, but by how the light plays across its surface. So let's step back and look at what we have built. We started with just 8 points floating in empty space. By connecting them into triangles, we gave them shape. By using barycentric coordinates, we found a way to fill that shape with pixels. By applying perspective correction, we gave those pixels depth. And finally, by adding lightning, we gave the object volume and touch of realism. It is a pipeline, it is a specific sequence of mathematical operation. Matrix rotations, cross products, and the dot products stacked on top of each other. Every 3D video game, from the simplest indie title to the most realistic AAA titles, is doing exactly this. They just do it on dedicated hardware that can run these calculations billions of times a second. But the logic remains exactly the same. If you like this, you can take a deeper dive into the cube itself in the video here. We discuss in detail how the model is actually described, defined, and how the rotation works in principle in 2D and 3D. That would be all for today. Thanks for watching. If you want to see more in the future, don't forget to hit the subscribe button. And ciao!